Hi, this is Algebra 2, Lesson 89. We're going to talk about conjunctions and disjunctions and the products of secants and chords. We're starting on page 368. Okay, conjunction. The con means with or together, and junction means join. So a conjunction is where there are two or more restrictions on the variable, and they must join together at the same time. So we're going to use the word and. So, for example, we're doing inequalities. So, graph negative x minus 3 is less than or equal to 2, and x minus 2 is less than 1. And our domain is integers. Okay, so both of these have to be true. So let's start with this guy. Negative x minus 3 is less than or equal to 2. And we're going to solve for x. So we can add 3 to both sides. Negative x is less than or equal to 5. We want to solve this for x, so we're going to divide the whole thing by negative 1, which remember is going to flip the inequality around. So x is greater than or equal to negative 5. And we're going to solve for x on this side. X minus 2 is less than 1. So plus 2, and x is less than 3. Okay, so now we have x is greater than, I need to actually extend this line, don't I? Sorry. X is greater than or equal to negative 5, and x is less than 3. Our domain is integers, so it's not the spaces between the lines. Let me use the red. The x could equal negative 5. Okay? It's not going to be the space in here because those are not integers. But it could be negative 4. It could be negative 3. It could be negative 2. It could be negative 1. It could be 0. It could be 1. It could be 2. It cannot be 3 because x is less than 3. So this would be your graph. It is all of the integers between and including negative 5 and less than 3, but not including 3. So that would be your graph. Okay, let's try another one. We have the graph of negative 2 is less than x minus 2, which is less than or equal to 4. So we could have written this the same way and put the x's in the middle. This gives us an x minus 2 in the middle. So we still need to solve for x. So we can break this into two pieces. We have negative 2 is less than x minus 2, and we have x minus 2 is less than or equal to 4. Our domain is all real numbers, and we need to solve for x on both sides. So over here, if we add 2 to both sides, then this cancels, and we have 0 is less than x. Okay, that was pretty easy. On this side, we can add 2 to both sides, and we have x is less than or equal to 6. Okay, so our domain is all real numbers. 0 is less than x. So we can put an open circle on 0 because it's not going to equal x. And x is less than or equal to 6. So we can put a closed dot on 6 because it could equal 6. And then we're going to fill in this line. And that is our conjunction. These are the real numbers where both of these equations are true. Okay? Next, we're going to talk about disjunctions. Dis means not, and junction means join. So these are going to be inequalities in which it's not necessary to satisfy all of the restrictions on the variable, just one of them. Instead of using the word and, we are going to use the word or. So, here's an example. We're going to graph negative x is greater than or equal to 3, or negative x is less than negative 1. The domain is in the real numbers. So, we're going to start the same way. We're going to solve for x in both of these. So we have negative x is greater or equal to 3. We have negative x is less than negative 1. To solve this for x, we're going to divide both sides by negative 1, so that's going to flip the inequality. So we'll have x is less than or equal to negative 3. On this side, we're going to divide both sides by negative 1, which is going to flip the inequality, so we'll have x is greater than 1. Notice both of these cannot be true. But since we have an or, we only need to satisfy one of them. So, if we graph x is less than or equal to negative 3, and our domain is real numbers, that means we can put a closed circle here, and x is going to either equal that or it's going to be less than that. It's going to go this way. Or x is going to be greater than 1. It's not going to equal 1, but it's going to be greater than 1. So this is our graph. And the answers are not the things in between. They're on both sides. None of these answers fit this disjunction. Okay, let's try this one. We have negative x minus 2 is greater than or equal to 0, or x plus 3 is greater than 6. Our domain is in the integers. Okay, not real numbers this time, integers. Okay, so let's solve for x. We have negative x minus 2 is greater than or equal to 0. Let's add 2 to both sides. And negative x is greater than or equal to 2. Now we're going to divide negative 1 on both sides to get rid of this negative, and we're going to flip the inequality so x is smaller than or equal to negative 2. Or x plus 3 is greater than 6. Subtract 3 from both sides, and we have x is greater than 3. So x is either less than or equal to negative 2, or x is negative 3, and we're talking about integers. So for the integers that are less than or equal to negative 2, that could be negative 2, or negative 3, or negative 4, or negative 5, or negative 6, and we're going to continue in that pattern. Or x can be greater than negative 3. We don't need to put a dot there because we're only doing integers. So we're going to just put closed dots on all of the integers that are greater than 3 and a big arrow here to show that it continues in that pattern. So the answer is either an integer that is less than or equal to negative 2, or an integer that is greater than 3. Okay? Okay, now we're going to talk about the product of chords and secants. So a little review. A secant is a line that bisects a circle. It goes through a circle. The chord is the segment of the line that is inside the circle. A tangent touches a circle at one point on the edge of the circle, but it doesn't go inside of the circle. Okay? And let's look at page 370 in your book. The last time we talked about chords, secants, and tangents, we were talking about the angles at which the chords, secants, or tangents met. So, to review, when two chords intersect, and of course they're going to intersect inside circles, the measure of the vertical angles, that would be this angle and this angle, equal half the measure of the intersected arcs. So, 80 plus 90 divided by 2 is going to equal 8.85. And that's actually the angle of this angle the measure of this angle and the measure of this angle, because they're going to be equal. Okay? Here we have a secant and a tangent, meaning outside the circle. So when two secants, or two tangents, or a secant and a tangent, intersect outside the circle, the measure of the angle formed, this angle, is 1/2 the distance, or the difference, sorry, of the outside arc and the inside arc. Right? So this angle is 170 minus 90 divided by 2, which equals 40. Okay, in this lesson, we're actually going to talk about the lengths of the segments instead of the angles at which they meet. So, here we have two chords intersecting inside the circle. The products of the lengths of the chord segments are equal. So, this segment is 4 and this segment is 3. On this side of the intersection, this segment is 2 and this segment is 6. And so this is saying that 4 times 3 equals 2 times 6. Okay? Which of course is true. This would be 12 and this would be 12. If we look at this line, this segment is x and this segment is 5. This segment is 3 and this segment is 7. So 3 times 7 is going to equal x times 5. And then we can solve for x. It would be 21 divided by 5. Okay? When secants intersect outside the circle, like this, the product of the whole segment, so from the intersection to the outside arc, the product of the whole section and just the outside section, the external segment is what this calls. So from the intersection to the inside arc. Okay, so the products of the whole segment and the external segments of both lines are going to be equal. So in this case, that would mean that 3, because that's the outside part of this, times 8, because 3 plus 5 is 8. So 3 times 8, which is 24, is going to equal 2 times 12, which is 24. Okay, in this case, we're going to say the length of the outside segment is 3. The length of the entire segment is 3 plus 5, which is 8. The length of this outside segment is 4, and the length of this entire segment is 4 plus x. So this is going to be 4 times 4 plus x on this side, and 3 times 3 plus 5 on this side. So 4 times 4 plus x is going to equal 3 times 8, which is 24. Okay? And then you can solve for x. If a secant and a tangent meet, then we're going to find the product of this secant the same way. We're going to take the outside segment times the entire segment, which is 4 plus x. So 4 times 4 plus x. For the tangent, we're just going to take the point of intersection to the point where it actually touches the circle, and we're going to square it. So this will be 8 squared. Okay? To summarize, when chords intersect, the product of the chord segments are equal. When secants intersect outside the circle, the product of the entire segment and the external segments are equal. If a secant and a tangent intersect, the product of the entire secant segment and the external secant segment equals the square of the tangent segment. The rest of the lesson is going to show very nice proofs of these rules, and I do want you to read them and understand them. for the sake of this video though, I just want to show you how to work the problems. Okay? So instead of going through the proofs here, I want you to read them on your own. Let me know if you have any questions about them. And right now we're going to go through the practice problems on page 372 that have to deal with chords and secant and tangent segments. So on page 372, we have this circle, which is intersected by two chords. The chord rule says the product of the chord segments will be equal. Okay, so this chord segment is x and 7, and this chord segments are 4 and 3. So we can say that 4 times 3 is going to equal 7 times x. So 7x equals 12, so x equals 12 sevenths. Okay? If you look at this, this is 1 and 5 sevenths. And if you look back at the picture, you can see that this is a reasonable answer. X is this little segment right here. And if you kind of break this off and put it here, you can see that it's just a little more than half as long as this segment, which of course would be 1.5 because this is 3. So it's going to be just a little bit bigger, a little bit smaller than that segment, a little bit smaller than 1.5. I mean a little bit bigger than 1.5, so it's 1 and 5 sevenths. Okay? It's a reasonable answer. It's good to think about that and whether the answer you came up with is reasonable. Okay. So that would be the answer to practice problem C. Let's look at practice problem D. We are finding y, and here is the problem. We have a secant and a tangent. And our secant tangent rule says that the external segment, when we multiply the external segment of the secant times the entire length of the secant, that is going to equal the external section of the tangent squared. Okay? So 4 times 4 plus y is going to equal 6 squared. So 4 times 4 plus y equals 6 squared. Okay, now we're going to solve for y. 16 plus 4y equals 36. Subtract 16 from both sides. And 4y equals 20. So y equals 5. And if you look back at the picture, 5 is a reasonable answer. It's a little bit bigger than the external segment. It's a very reasonable answer. Okay? That is it for this lesson. Read the proofs carefully until you understand them. Let me know if you have any questions. Do the other half of the practice problems in your homework. Thank you very much.